Well, it's a great honor for me to be here. I visited the city once in 1985, which was a while ago. All right, so I don't have a particular agenda for this talk, so I'll just proceed and we'll see how it goes. So I'll first introduce to some extent the setting of the classical Langlands, and then we'll pass to the geometric picture. So Langlands takes place over global fields. There are two kinds. There are number fields and function fields. And so because we're interested in the geometric story, we'll be dealing with function fields. So we'll be working for the first part of the talk over a ground field, which is a finite field Fq, and we fix a curve, smooth projective over Fq. And to simplify, we'll be working with, well, in principle, the story works for an arbitrary reductive group G, but we'll be working with GLN. And the object of study is something I'll call BUN-N. So well, I'll suppress the notation that has to do with the curve X, but I'll write it of Fq. So this is the set of isomorphism classes of rank n vector bundles on the curve. And so this is a set, and we'll be interested in a certain linear algebraic object, which is just a space of functions on the set. So there is a certain line below which it's not visible for people in the back rows. So you tell me which. So is this okay above this line? Well, no, I'm asking people in the back row. One solution will be for the people to back row to come closer. In this case, the problem will be resolved. All right, let me just write it like this. I'll write, say, functions on BUN-N of Fq. Just so for this part of the talk, you can talk, well, you could talk about functions with coefficients in C or in an arbitrary algebraically closed field of characteristics 0. So the story will be essentially algebraic. All right, so what we're going to do, we're going to introduce a huge family of pairwise commuting operators called Hecky operators. So the parameters are places of the curve. So let X be a place, i.e. a closed point, and we'll introduce a Hecky operator. It's called Hx. So it will map from the space of functions to itself. And so it was introduced already in talks by Pantev, Donaghy, and Simpson. Let me just recall. It's defined geometrically. It's defined by a correspondence. So we'll introduce, I'll use the curly H. It's called the, well, also write of Fq. It is the Hecky correspondence at the point X. It's a certain set, which I'll define in a second, equipped with two projections to this set of isomorphism classes of bundles. And so my notation for this is H left and H right. All right, so let me say what the set is. Oh yeah, I should keep track of the time. So when did I start? Okay. And it's 1 hour, right?
Yes.
All right. So what is this new set? It's the set of triples. So one element of the triple is a rank n bundle. Let me call it M. Another element is another rank n bundle. I call it M prime. And the third is an embedding of M into M prime. Call it alpha. It's an embedding as coherent sheaves with a condition such that, it's an embedding of coherent sheaves on the curve of the same generic rank. So the quotient is necessarily torsion, and the condition is on what this torsion looks like. The condition is that the quotient is isomorphic to the skyscraper at the point x.
But they're not fixing the isomorphism.
No. Isomorphic in some way. So now you can fix an M, and you can ask how many ways. You can ask what's the fiber of this map. Let's say this projection sends this triple to M, and this projection sends this triple to M prime. So you can fix an M and ask what is the fiber of this map over a given M. Well, it's a little exercise to see that. So this fiber, the set of ways to complement a given M to a triple, is the set of F cubed, it's the set of points in the n-1 projective space with coefficients in the residue field at the point x. More precisely, let me just write it somewhere, more canonically, the preimage of the given F, M, is the space of points of the projectivization specifically of the fiber of M at this point. It's the lines in, so you take this rank n vector bundle, you take its fiber at the point x, it's a n-dimensional vector space over the residue field, and this is the space of lines in this vector space. And a similar thing will happen to this projection. So the fibers here are, again, points over some finite fields of projective spaces. So we're finally ready to define this Hecky operator. It's defined by the procedure of pull-push. So I should write it somewhere. So the Hecky operator, Hx, is defined as follows. If you apply to function f, so let me write it, and then I'll comment on the notation. So you start with the function, you pull it back, you get a function here, and then you sum it up along the fibers of this map, and it's a finite summation. So, and there is a normalizing factor one has to put here. I think it's minus q1/2 to the power, I think n-1, something like that. All right. So, and it's very easy to see that these operators for different choices of x commute with each other. And so the problem that one wants to solve by, well, basically based on an analogy with number theory, is to find the joint spectrum. Technically speaking, you will not be interested in the entire space of functions. You restrict the space to a certain subspace that consists of what's called cuspidal functions. I would be happy to give you a definition, but after the talk, because it's not that it's technical, but it'll just divert your attention. So inside the entire space of functions, you introduce a subspace that will denote in this way. And it's invariant under these operators, and so you can rig this definition in such a way that the on this subspace, the action of these operators is locally finite. So in other words, every vector is contained in a finite dimensional subspace invariant under all these operators. So the diagonalization problem is well posed. And you can also see that these operators are actually diagonalizable. So, all right. So here's what the Langlands conjecture used to say, but now it's no longer a conjecture, it's a theorem due to the work of two brothers Laforgue. So let me just let me state those theorems. So maybe before I need one more piece of notation. Well, and that's where the Langlands picture comes into the game. So let's sigma. Well, now we're getting into somewhat more technical mathematics. It'll be a representation of the étale fundamental group of X into GLN of QL, let's say bar. So now let me say that I'm assuming that the coefficients of our functions are QL bar. So there's one thing to know about representations of the étale fundamental group, and this is something that we're going to exploit further in the lecture, namely that if you have a point of the curve, you can evaluate the sigma and what's called the Frobenius element of the fundamental group. This element is defined up to conjugacy, and what you get is a well-defined conjugacy class. But in particular, so the eigenvalues of this matrix are well defined. And in particular, the trace is well defined.
What is it used there? And that word GLN, what is there? Is there Q?
Where?
Q bar of, at what is there?
QL bar?
L is some kind of another prime?
Yeah. It's some prime different from P. So here is theorem 1, which that every system of joint eigenvalues of the operators Hx comes from a sigma. So let me explain what this means. So if you have a sigma, I can produce a collection of numbers parameterized by the points of the curve. Or let me say it like this. So i.e., so if you have an eigenvector, then all these coefficients lambda x are of the form they are obtained as traces of this Frobenius elements. So just say that a choice of sigma, according to what I said here, defines a family of elements of QL bar parameterized by points of the curve. Namely, you take these elements, you take their traces. For each x, you get a trace. And the claim is that every element of the joint spectrum appears in this way. So these lambdas must be of this form. So this is theorem 1. And so here is theorem 2, which is stronger. Yeah, let me just say that. So this theorem 1, the way I stated it, makes sense for GLN, but in fact, you can do the exact same thing for arbitrary reductive groups. Let me just say for any G. And theorem 2 is actually specific for GLN. So every sigma, every irreducible sigma does appear as a system of eigenvalues and moreover the corresponding eigenspaces are one-dimensional. So let me put some attributions. So, well, for GLN, theorem 2 obviously stronger than theorem 1, but as I said, theorem 2 is specific for GLN, and this is general. And so this is Vincent Laforgue, the year, well, this paper underwent a series of evolutions, I guess, 2013. And this is his older brother. This is Laurent. So roughly 2001. And at the same time, I should say that it's not immediately evident, but it's also true that this theorem for GLN actually implies this theorem. And I'm even going to say something about the proof of theorem 1. So they're proved. It's a remarkable mathematical story. They use the same geometric ingredient for both proofs, namely this geometric object called Stuka invented by Drinfeld, but they're used in drastically different ways. Somehow Laforgue, the elder who followed Drinfeld, used them statically, and Vincent used them dynamically in a completely original and kind of groundbreaking fashion. So his paper is really this masterpiece. All right. So in some sense, these theorems, well, in some way they are the best you can hope for, but it's not exactly geometric Langlands. Geometric Langlands is something else that predated both of these theorems. It was invented by Drinfeld in the early 80s as a way to, well, prove something in the direction of theorem 2. And that gave birth to a field of mathematics of its own. So I'll explain it in a second. So is Drinfeld's partial solution to theorem 2, which was published around 1983. And so here is what it's about. So we'll have to revisit the story about Frobenius elements. So I'll remind you of the following general story that was invented by Grothendieck, and it says the following. So let Y be an arbitrary scheme, or slightly more general than a scheme, we'll actually need algebraic stacks. So over a finite field FQ. So in this case, one can talk about the category of elladic sheaves on Y. So to Y, one attaches, and let me call it D of Y. I'll write it right away. It'll be the derived category of constructible elladic sheaves. So, and what Grothendieck says is that if you start with an object of this category, call it capital F, to this F you can attach a function on the set of FQ points of Y. Let me write it. Funct of F, and it's an element in the space of functions on the set of FQ points of Y with coefficients in QL bar. So this construction is a very close relative of the procedure that I mentioned a few minutes ago when you start with the representation of the étale fundamental group and you take traces of the Frobenius elements. In fact, it's exactly this generalization of this. So again, I would be happy to review this construction, but maybe not in the main time of the talk. So it's some procedure that performs this operation. And so let me say a few words of how this procedure behaves, and maybe in the process I'll even reveal the nature of this procedure. So here are the two main properties. So suppose you have a map of algebraic varieties y1 to y2. Let's call this map H. Well, at the level of categories, there are two things you can do. There's the operation of the pullback of sheaves, and there's a procedure of direct image. So well, we'll be using pullback with a star and direct image with compact supports, whatever these guys are. So if you're familiar with these operations in topology, these are very close analogs. Note that I wrote as if these functors are adjoint. In fact, they're not adjoint. Okay, so this is on the one hand. On the other hand, well, something we already used, you consider the space of functions on FQ points of Y1 and the space of functions on FQ points of Y2. And these spaces are also related by similar procedures. If you start with a function here, you can pull it back. Oh, sorry, it's H. And you can also, if you start with a function upstairs, you can sum it up along the fiber. And so the main feature of this assignment is that these operations are compatible. So if you start with a sheaf here, you can pass to a function and pull it back. It's going to be the same as if you pull back the sheaf and pass to the function. Well, this is more or less tautological from the definition, and what's a deep theorem, which is known as the Grothendieck-Lefschetz trace formula, it says that if you start with a sheaf, pass to a function and sum it up along the fiber, it's the same thing as if you push forward the sheaf and pass to the function. And by the way, well, the first property actually tells you what this procedure is, namely, so if you think about it, you'll see that it's enough to construct this procedure in the specific case when y is the point. Name the spectrum of FQ. So, and I leave it to your imagination to construct. So, well, let me say that D of point is complexes of vector spaces equipped with an automorphism, which is that Frobenius finite dimensional vector spaces. And what this procedure does in this case is just you take the alternating trace of the Frobenius elements on this cohomology of this vector space. Just a side remark. All right. So with this introduction, let me tell you what Drinfeld proposed to do. All right. So it'll be kind of converse to theorem. Well, it's in direction of theorem 2. So we start with sigma, which is homomorphism from the étale fundamental group of the curve to GLN. And technically, we'll assume it's irreducible. And we would like to produce a non-zero eigenvector. So we want to see that the corresponding eigenspace is non-zero. An eigenvector for this Hecky operators. Let me call it F sub sigma. So i.e. F sigma is a function that satisfies such that H sigma of sigma equals trace of sigma Frobenius x times F sigma. So that's what his paper did when n equals to 2. And so it's a very non-trivial problem before the work of the two Laforgues. Just you have to cook up an eigenvector. Well, an analog of this problem over number fields is equivalent to Taniyama-Wei conjecture. So it's got to be non-trivial. Well, in that case, you're trying to produce a modular form. In this case, it's, well, a geometric counterpart of this modular form. So it's very difficult to construct it by hand. And what Drinfeld proposed is to use geometry, namely Grothendieck's dictionary, to construct this function. So here's what he did. So I should also say that kind of maybe the primary idea of Drinfeld's approach goes back to André Weil. So he did it for GL1 or something equivalent. So the first observation, which is also due to André Weil, is the following: that what we denoted Bun of FQ is actually Bun of FQ. So what do I mean by this? So I mentioned before that if you have an algebraic variety, you can, over FQ, you can consider the set of isomorphic classes, a set of its FQ points. So now there exists a geometric object. It's not quite an algebraic variety, it's an algebraic stack, but it's not actually so different, called bun n. And so if you came to this conference, that it has appeared a bunch of times. So it's the moduli space of rank n bundles on the curve X. And this is the bun n that I write here. And then you can take its set of FQ points, and you will see that the set of FQ points is exactly the set of isomorphism classes of rank n bundles on the curve. And so Dinfeld said, how about instead of constructing an element of the space of functions here, how about we try to construct an object of the derived category? Construct F sigma, which is an object of the derived category of L-adic sheaves on this moduli space, such that the corresponding function will be an eigenvector with eigenvalues given by sigma. But so then the next question he asks himself is that can we encode the property of the function being an eigenvector by some property of the sheaf itself? So he asked this question, and he came up with a kind of very beautiful answer. So namely, remember, when I introduced my Hecky functors, I used a curly h, which was a certain correspondence. But I also wrote h of fq, and that meant to hint that, in fact, it also came as a set of fq points of a certain geometric object. So there exists a moduli space hx called the Hecky stack at the point x, and it's the moduli space of triples that I wrote before. Just instead of taking FQ points, I'm regarding the modular problem. And well, it's an object of algebraic geometry. We can now use a functor. I denote it by the same symbol h sub x. It will be a Hecky functor. It will, same as before, I pull back and push forward, but in the setting of sheaves, well, and technically there is a Tate twist here. Remember, I put a coefficient, so you twist it by n minus 1 over 2, and cohomological shift by n minus 1. So, and this hx is a functor from this category to itself. And so we'll now encode the property of the function that we want to establish by the corresponding property of the sheaf. So here's how this property of the sheaf reads on the first iteration. So what we want is that if you apply this functor to your sheaf f sigma, you'll get something beautiful. So instead of, before we multiplied this function by a scalar, but in this case, what we'll do, it doesn't make sense to multiply an object of the category by a scalar, but you can tensor it by something. So what we'll see, let me write it like this and I'll explain. So the result of the application of this functor to the sheaf is the tensor product of my sheaf by a vector space, and that vector space is, if you wish, the fiber of that. So let me just say it like this. So a representation of the fundamental group can also be thought as an elliptic sheaf on the curve, and I'm taking the fiber of that elliptic sheaf at the point x. It's an n-dimensional vector space. So this is called the Hecky property of this F sigma, and we will say that F sigma is a Hecky eigensheaf with respect to sigma. So kind of the notion of Hecky eigensheaf has many advantages over the notion of eigenvector in that, and so the main advantage is that so the sigma comes as is. We don't take traces of the Frobenius. It really appears, well, kind of as it comes, as a low. Well, it'll be especially evident once I go from the first approximation to the second approximation. So in the second approximation, what I want to do, I want to allow this point x to move along the curve. So, namely, I'll make this point x a parameter. I'll introduce kind of the big Hecky stack, which will map to, well, it'll have three projections. It'll have a projection to ban m that I still denote by h left. It'll have a projection to ban m, which I'll call h right, but it will also have a projection to the curve x. And the old Hecky stack is the fiber of this one over a given point. And I'll now introduce a big Hecky functor. It will go from the category of sheaves on ban n to the category of sheaves on the product on ban n times the curve. And what I do now, so I still pull back, but I push forward with respect to the projection on the two factors. So I pull back with respect to this projection, and then push forward onto ban times x. And so also Tate twist. And so the modified version of the Hecky property, which is much more powerful than this one, says that what I want is that I want h of f sigma to be actually the tensor product of f along the Bann factor times sigma along the second factor. All right. So Drinfeld said that, well, instead of solving the function theoretic problem, we'll be now solving a geometric problem of looking for a sheaf, well, more generally an object of the derived category, that satisfies this property. And that's how the field of geometric Langlands was born. So it became the search for such sheaves f such sigma attached to an irreducible local system sigma. All right. So let me state a theorem, and then I'll spend the rest of my time on kind of variants and generalizations.
Is there a symbol star S or something?
Sorry, my handwriting. It's H times S. So I pull back with respect to this one. and I push forward on these two factors. H cross S. All right. So one indeed can prove the existence of such F sigmas. So this is theorem. So Drinfeld for n equals 2, as I said, 1983, and it's Frankel, Villen, and myself for any n around the year 2000 is that for every irreducible sigma, there exists a non-zero F sigma that satisfies the Hecky property. All right.
You said that previous theorem is 2001, which evidently follows from this. Right? Oh, no, sorry, I want to say Laforgue's theorem.
No, Laforgue proved more. He.
You mean multiplicity one?
Well, multiplicity one follows. So this is what covers what's called the unramified case. Yeah. So one can deduce what he. So one can deduce that direction also from this. But so Laforgue the Elder proved, in fact, both directions. This only does one direction.
It's only for real unramified.
Yes, but that can be that can be overcome. But this only does one direction, whereas the initial Laforgue's work establishes both directions. All right. So now let me make some comments.
The all over finite fields is still?
Say again?
It's still over finite fields?
Yeah. So that's my first comment. So if you look at this statement, unlike the function theoretic one, it's not linked to our field being a finite field. So this makes sense over an arbitrary ground field and basically in any sheaf theory. So, well, over arbitrary ground fields, you can work with elliptic sheaves and you can ask for the existence. Well, sigmas make sense. And you can ask for the existence of this Hecky eigensheaves, and so this theorem applies in arbitrary geometric context. So let me just write it. Remarks. So one, the search for F sigma makes sense over any ground field. Let's say as long as we work with elliptic sheaves. But also, and it's something that we've seen at this conference, is that you can actually change your sheaf theory. So if you're working over ground field of characteristic 0, instead of talking about elliptic sheaves, you can talk about another sheaf theory, and that is the theory of D-modules. Can ask the same question for D-modules instead of elliptic sheaves. And it turns out that this leads to a lot of interesting and rich mathematics, kind of beyond the scope originally envisioned from the point of view of number theory. So let me make a few remarks about this. And this is, again, something that we've seen in this conference. So continuing in this direction, so let's say from now on we'll be interested in the context of D modules. So let me put it into the framework of what was happening at this conference. So, Donaghy, Pantev, and Simpson work specifically over C. And they want to invoke analytic methods in constructing this F sigma. So what they said, so they invoked non-abelian Hodge theory. So they used the following. They started from sigma, and they replaced it by sigma Higgs. So this is a transcendental operation, non-abelian Hodge theory. Then they went from sigma to, let me call it F sigma Higgs. And so as was explained in detail in Ron's lectures and in Tony's lectures, so this is some abelian procedure. And then they applied a still very mysterious operation. So this is non-abelian Hodge on the curve, and this is non-abelian Hodge on BUM, in which this is something much more complicated. So they went this route to get from sigma to F sigma. And well, and as we've seen in Tony's and Carlos's lectures, this is still kind of very difficult to realize technically. But obviously there's much more structure, because although the operation is transcendental, we know that if you go from sigma to F sigma, this is actual algebraic. That means that for some mysterious reason, with the transcendental procedure that they preserves the action of the Galat group of C over rationals. All right, so this is one comment I wanted to add. And there were some developments that led to this. So this was Kapustin-Witten, who realized that this procedure of going from sigma to F sigma also follows from quantum field theory. All right, so this is one comment. Another comment is that one can try to expand this picture kind of a great deal as follows, if one stays within the context of D modules. So So in this case, in addition to what we call BUN, one can introduce another algebraic geometric object called log-sys N. So this is the moduli space of n-dimensional local systems on the curve. And so what we call sigma was just a point here. So in what we saw, that to a point in this log-sys, one can attach an object of the derived category of D modules on BUN, but one can try to do it in families, and one arrives at the following much more ambitious conjecture, what it's called the categorical geometric Langlands conjecture. And it says the following. Again, it will be a rough approximation, so there's a correction needed here that Ron mentioned in his talk. So we consider this geometric object, log-sys, and we consider the derived category of quasi-coherent sheaves in it. We write it like this.
It's also a stack, yeah?
Yes, it's also a stack, on the one hand. On the other hand, so we consider this BUN, we consider the derived category of D modules on it. And so what we did before, to a particular point here, we attached an object, but what we want now is actually an equivalence of categories.
And sorry, again, about this bond. So you consider all bundles without any kind of
yes.
semi-stability.
Correct. It's the entire stack.
Yeah.
And it,
unseparable.
Yeah, and not, it's non-separated. Yeah. And you need it. Yeah. So otherwise, nothing can work unless you do the entire thing.
Yeah, yeah.
And so, well, this is kind of a significant conjecture. Let me just say that for n equals 1, it's easy to, well, so it's equivalent to the Fourier-Mukai transform. So in some way, this conjecture is a non-abelian version of the Fourier-Mukai transform. And, well, as scary as it sounds, some significant progress has been made towards this conjecture. I call it Quasi Theorem because it's kind of, it's done modulo, it can be proved modulo some technical work. And so in the case of GLN that I'm talking about here, for other groups it remains wide open.
So Hecky condition, how is it going to be work here?
Well, it's a very good question. So here, okay, now that you asked, well, I'll answer this question because you asked. So there are functors that work, that act on the right-hand side, and they, let me say it like this. For every point x, let me do it not in families. There are these Hecky functors that I introduced here. And so the claim is that under this equivalence, these functors are supposed to correspond to some particular family of functors here, also indexed by points of the curve. And let me tell you what they are. Let me just, okay, let me say it without writing. So these functors are given by tensoring by a particular vector bundle for each point. And this vector bundle is the following. Let me just write it. For each point of the curve, there is a map from the stack of local systems to what we call the classifying stack of GLN. So you can take a local system and take its fiber at the point x. So the classifying stack of GLN has a canonical vector bundle, the tautological bundle. And you can pull it back and obtain a vector bundle here. And now on this category of quasi-coherent sheaves in the stack, there is an endofunctor given by tensoring with that canonical bundle. And that is supposed to correspond to the Hecky functor on the other side. But I mean, there is much more to specify by this equivalence. We know quite a bit what corresponds to what under this equivalence. All right, so there's obviously much more to say, but maybe I'll prefer to stop here 3 minutes before time, and then if people want to ask, well, I'll be happy to. Well, again, there are many directions in which one can comment and generalize.
Other questions, remarks?
Well, you have some modification of the left-hand side, right?
Yes. You want to know what it is, or
no,
you know what it is?
Just a statement to be, I mean.
Yeah. So this is not correct as stated. So, and here some non-trivial homological algebra comes in, which one talks about not quasi-coherent sheaves, but what's called int-coherent sheaves with specified singular support. And that has to do that the original Langlands conjecture, well, what parameterizes automorphic forms is not Langlands parameters, but what's called Arthur parameters. There is this Arthur SL2 which measures to the degree of non-temperateness. And miraculously, this has an incarnation in the geometric world by some quite non-trivial homological algebra. And that's responsible for this modification. It's very remarkable that this Arthur SL2 has to do with singularities of the stack of local systems.
So, and are there any corollaries from the original question? Yes, so if you can answer for a curve on this question, what are the corollaries? What you can prove from this?
So one thing that, Drinfeld was able to deduce, he was able to deduce Kashiwara's conjecture. That if you start, if you have a proper map between algebraic varieties, if you start with an irreducible perverse sheaf, if you take its direct image, then basically the decomposition theorem.
So here you consider, and everybody, I mean, that in geometric Langlands consider curve. I mean, we start from curve. What about any kind of
surface?
Surface or
it's wide open. So no one really knows.
You mean that it's related to high identity?
Well, there are some obvious obstructions to trying to generalize this story. If you try to think about it, you'll see that as is, it doesn't work. And, we can talk at length about this. So I'm inclined to think that Langlands is something specific to algebra geometric dimension 1.
Mm-hmm.
That's because that's where it lives. And this is also suggested by physics, that kind of, this is the dimension where this phenomenon occurs. In the abelian case, you can do higher rank. You can do higher dimension. But the non-abelian story, there is a chance that it's just linked to algebra geometric dimension 1.
Any other questions? Sorry, this categorical geometric Langlands you have formulated for only GLN?
No, there's a conjecture for an arbitrary G, but
it's not an equivalence.
No, it's an equivalence. Yeah, there's a conjecture about an equivalence for an arbitrary G, but there is an outline of the proof, which for GLN, the only remaining steps to do are technical, but for an arbitrary group, there is a certain one step that says that some functor is fully faithful, and we don't know how to do it. Except in the case for GLN, where you can place Whittaker models. And so basically, the reason we can do it for GLN is that we have a much better control of the Whittaker model.
So you just said about this categorical
yeah.
And your theorem of 2000, is it generalized for arbitrary G?
No, it's the same bug.
But for,
yeah, it's for GLN, for the same reason. So the reason we can do it for GLN is because we can control the Whittaker model.
So my question is related to the first one. So is there some work for some particular groups apart from GLN? So I figured that you hope to do it in general, so there is. You think that the proof should work in general?
Yes.
But we know that in the usual Langlands there is a lot of progress on SP4. So is there something similar in this?
So there is work on SP4, but it's not conclusive. You still can't do it.
But you think it makes sense to consider?
Yes, I do make. Yeah. So.
What about SL2?
It's still difficult. I mean,
SL2.
yeah. So going from GL2 to, so if here, if this is GL2, PGL2, it's okay. But if here you have SLN, there's trouble. So even type.
The usual program also is a problem.
Yeah, yeah. So
same problem.
Yeah.
More question? Then let's end this thing again.